Okay, all I wanted to say is to welcome back. Let's check my camera a little bit. Okay. Now, as I said, I want to look at analytical methods for engineers. Okay, and this tutorial is the sinusoidal function. Okay. Now, this I'm not going to read out to you overall. Okay, that's something you can hopefully you can read for yourselves at your leisure. Okay. Let me make sure that I can get it all the way up. Bring the angle along. Okay, so we get this inline and under. Okay. You should judge your progress by completing the self-assessment exercises. Now, that is important for you to be doing for yourselves. Look at the exercises. Do them, write them out, okay? Trigonometry has been covered in the NC Maths module and should have been studied prior to this module. This tutorial provides further studies and applications of that work. Okay, now some of the work overlaps, so be aware of that. So you'll see bits on this that you've seen probably before if you have done the other pieces of work that I've put up. Okay, I'm going to try to get these to follow on when I upload so that they're not scattered over the channel. Okay, I'll try that and see what happens. Now, radian. In engineering and science, we use the radian to measure angle as well as degrees. This is defined as the angle created by placing a line of length 1 radius around the edge of the circle as shown. Here we are. Okay? And that's all 1 rad. Okay? This angle is called the radian. The circumference of a circle is 2 pi r. It follows that the number of radians that make a complete circle is 2 pi r over r, or 2 pi. There are 2 pi radians in 1 revolution, so 360 degrees equals 2 pi radian. 1 radian equals 360 divided by 2 pi equals 57.296 degrees. Now it's okay, I'm just looking at, and I think this is something you should look at dividing yourselves and putting into your calculator to make sure that you agree with this resultant answer here. Okay, I'm not going to do the answer for you basically because you should be able to do this now at this level. Okay, what I'm trying to do here is to provide you with learning materials that can enrich your own knowledge and make you probably more proficient or better than you thought you are, hopefully. Okay. Two-dimensional coordinate systems, Cartesian. In a two-dimensional system, the vertical direction is usually it's okay, sorry, I missed I thought I might have forgotten to do something on my camera. Okay. Is usually y, positive up, and the horizontal is direction is x, positive to the right. Other letters may be used to designate an axis, and they don't have to be vertical and horizontal. Okay. The origin O is where the axis cross at x equals 0 and y equals 0. A point P on this plane has coordinates x and y, and this is usually written as P x comma y in closed brackets. Okay. Now you notice that we mentioned Cartesian. Here we're now going to mention polar. Now polar, if a line is drawn from the origin to point P, it is a radius r and forms an angle theta with the x-axis. The angle is positive, measured from the x-axis in a counterclockwise direction. A vector with polar coordinates is noted as r, as you can see here. Okay. Okay. Sorry. Okay. Give me a light issue whenever it doesn't go right. Okay. Okay. Now conversion. The two systems are clearly linked, as we can convert from one to the other using trigonometry and Pythagoras theorem. Y equals r sine theta, x equals r cos theta. The angle I call theta, you can call it whatever you know or have been taught to call it. But that's the way I remember it. And just remember that it's your own style of learning. It's what triggers your memory to recognize a particular function or formula. Okay? It's just the way I refer to it. So you don't have to refer to it as I do. You refer to it as you know how. And here you have r equals x squared plus y squared raised to the power of a half. Okay. Now work example number 1. The xy coordinates of a point is 4 and 6. Calculate the polar coordinates. And here is your solution. And I was trying to remember this raised to the power of a half, how to get this result, but I do remember now. Remembering that when you raise it, it becomes your square rooting the end result value. And some of you probably know that a lot better than myself, because being an old man now, I had to try to remember it. Okay. Right. It's okay. Right. Okay, now these are self-assessment exercises. The answers have been given. Okay. Here. Okay. So make sure you write them out and you look at what you need to do to find the correct answers. And here, all we're doing here now is review of trigonometric ratios. Okay. That you can look for and look at for yourselves, and you should be familiar with all that already. Sine, cosine, and tangent. Okay. And thanking Mr. Dunn for his work excellently, and so forth. Here we have the inverse function. Now I'm not going to go for this, cosec, etc. This is for you to become familiar with, and you should already know a lot of this yourselves. Okay, sine and cosine rule. Okay, now here we're looking at example 2 solution. Okay, weight of 300 Newton is suspended on 2 ropes as shown. Calculate the length of the ropes. Draw the vector diagram for the 3 forces in equilibrium. Calculate the forces in the ropes. Okay, and here you have your solution. Okay, you've been given your solution here, so don't overlook it. Write it out, draw out the sketches, make sure you know what you're looking at and doing. And here we have the cosine rule. Okay, again, you should be familiar with all this yourselves already. And here we have example number 4. Sorry, what did I just look at just now? Okay, work number 3. Here we have work example number 4. Okay, and again, that is for you to look at and to write out. I don't need to go over this with you because you should be quite familiar with a lot of this already. And here you have a self-assessment. And with the answers beside it. But make sure that you try to understand how the answers were gotten, so that you know what you're doing when you're actually sitting in an exam room doing paperwork. Now here we have a sinusoidal functions. In nature and in engineering, there are many things that oscillate in some form or other and produce a repetitive change of some quantity. With respect to time, examples are mechanical oscillation and alternating electricity. In many cases, a plot of the quantity against time produces a sinusoidal graph, and the change is said to be sinusoidal. And here we're looking at that, okay? And we're showing you a mechanical example of that effect here, okay? So you have a Scotch yoke and eccentric cam. Scotch yoke, eccentric cam, okay? That's the cam that moves kind of like a jigsaw kind of thing, movement, okay? Now the Scotch yoke is a device that produces up and down motion when the wheel is rotated. The displacement of the yoke from the horizontal position is x equals r sine phi, r sine the angle, whatever the angle may be, okay, equals x r sine omega t. Plotting x against time or angle will produce a sinusoidal graph. The eccentric cam is really another version of this, okay? In all cases, we should remember that velocity is the first derivative of displacement and acceleration is the second derivative. It follows that displacement, etc., velocity, etc., acceleration, etc. And these are your formulas you will need to apply. Anything that obeys these equations is said to have simple harmonic motion. The starting point of the oscillation could be at any angle. So in that case, the equation becomes the starting point of the oscillation become displacement x equals r sine, etc. Velocity formula applied, okay? Acceleration, and you have your relevant formula for each. Now again, you need to look at the video to see what I'm talking about and look at what I'm doing. Now, yes, and it's just trying to show you that the starting point of could be at any angle. Okay, the angle is not set. Mass on a spring. A mass on the end of a spring will oscillate up and down and produce identical motion to the Scotch yoke without the rotation of a wheel. The displacement is x equals etc. The velocity of the mass is as given. The acceleration of the mass is again as given in the respective formulas. It can be shown for the frictionless case, in this case, where K is the spring stiffness in Newton meters and m the mass in kilograms. This is called the natural frequency. The natural frequency of oscillation is hence your formula here. Okay. Now we've all heard of centrifugal force. Okay, that is where an object is rotating and it exerts some force upon the body. It's what space astronauts have to go through and do before they can go into space. When a mass rotates at radius r, the centrifugal force is given by this formula. If this is a machine mounted on a platform as shown that can only move in one direction, the force acting in that direction is the component of the force in that direction. In this example, the force exerted on the spring is as given, and you can see that spring and you have a motion here, okay, and the spring is going to be exerting a force to try to prevent that from coming down onto it. So that force is going to be probably bouncing around a bit. And here you have work example number 6. Now again, I don't need to read this out to you. Hopefully you can read this for yourselves, okay, and deal with that. Write out the solution. Make sure that you understand the concepts behind it, and most of you should be able to do that by now, okay? And here we have the plot of x, v, and a. Confirm these answers, okay? Right? And work example number 7. I don't need to read this out again. You want... Okay, that looks good. Right, the end, yep, okay. Right, okay. That's for you to deal with and to take on. and to make sure that we have the right concepts of it. And again, here we have self-assessment exercise. Okay. Now, don't just write out the answers. Make sure that the answers are correct. Make sure you apply the relevant formula to find the solution to the question. Alternating electricity, right? Well, you're training to be electricians and engineers, so this should be familiar to you. So I'm not going to go for this with you. Don't need to. Or I shouldn't not need to anyway, basically. Okay. Again, we've covered this shortly, not so long ago. So again, I'm not going to go into this in any depth, okay? You can look at this for yourselves. And exercise here is for you to do, okay? And here we have complex waveforms. We covered this not so long ago at all. Okay. And yes, I think that's about us. Finish. And you can see that that's just a generated square wave there, basically. Okay. It's amazing the thing we can do with mathematics. Okay, thank you for your time. I hope you found this useful. Okay, let me just make sure I have all the information through, so I can go back and just to recap. Okay, just bear with me. I'm going to recap this. Okay. Okay, I'll now just going back through this, making sure that I have everything on my camera. Okay. Okay, thank you. I hope you found this useful. And again, this video is Analytical Methods for Engineers. Okay, thank you. Bye-bye.